So first, this is the outline for the talk. And first, we'll talk a little bit about the background information, like what is Hive, what is Spark, and why we want to do this project. And then next, we'll talk a little bit about the architecture and the design principles, followed by the challenges we had in the project, followed by the current status. So what we have accomplished, what we have accomplished so far, and what we plan to do in the near future. And so finally, there's some benchmark results. So I'll talk about the first 4 sections, and Chenxiang will talk about the final benchmark result. So this is background. So I think most of you probably have heard about Hive. Hive is a popular SQL engine on top of Hadoop platform. Basically, Hive on the surface offers a SQL-like language called HiveQL. So Hive users could write queries in that language, which would then be compiled by the Hive compiler and translated into Hadoop jobs. It could be MapReduce jobs, test jobs, and now Spark jobs. And I think almost all of you must have heard about Spark, because right now it's perhaps the most active project in the Apache community. So Spark is a data computing framework that is widely considered to succeed MapReduce. So major difference between MapReduce and Spark is that for MapReduce, it has to perform job in a strict 2-phase pattern. First map, then reduce. But for Spark, it offers much more primitives like reduce by, group by, union, filter, and so on. So in this way, it's more flexible. Also, for MapReduce, between stages, it needs to write intermediate result to temporary files on local disk. But for Spark, it doesn't have to do that. It can store the result in memory. So in this case, it is much faster than MapReduce. So the reason we want to do this project is because we think it can benefit users from both the Hive community and the Spark community. For Hive users, now they can have another alternative SQL engine other than MapReduce and the Spark and TEDS. Also, they can get some benefit in performance compared to MapReduce. For the Spark users, they can also now have another alternative SQL engine other than, for instance, Spark SQL. And so all the works for Hive on Spark are tracked by this JIRA, Hive 7292. This is also the most watched JIRA in Hive with about 180 watchers. So we also have efforts from both communities. Obviously, this is a Hive project, so most of the code change happen in the Hive code base. But from time to time, we also find ourselves in need of a new feature, or in need to modify existing feature in Spark. So we also have efforts on the Spark community as well. And we have also received contributions from many organizations besides Cloudera and Intel. Other organizations like MapR, IBM, and Databricks, they also have contributed to the project at a certain point. Uh-oh. OK. Go back. Go back. OK, so this is the design principles we have. So basically, we want to limit the code change to as few modules as possible. In particular, most of the code change happens in the physical plane generation and the task execution phase. The purpose of this is to have limited or no impact on the existing Hive code base and to lower future maintenance cost. As you know, Hive is already a very mature project, and there are a lot of existing features and optimizations. So in this way, we can almost get all the existing features and optimizations for free. So that's pretty good. And this is an overview of all the components we have at the moment in Hive. So you can see on the left side, there's Hive client, which could be a Beeline, JDBC, ODBC, and so on. So to use Hive, a Hive user first establish a connection between the Hive client and the Hive server 2 in the middle. And then the queries will first go through, we will go into the parser and get translated into AST. And the AST will go into a semantic analyzer and get translated into a tree of operators. So basically, operator in Hive is a basic unit of computation. So each operator, you can imagine that it just takes input rows from the upstream operators, does some processing, and then forward the rows to the downstream operator. And the operator tree will then get fit into the task compiler and get translated into a task tree. Finally, the task tree will get fit into the Hadoop client and submitted to the actual Hadoop platform for execution. Finally, the result we return back to the Hive client for the user. Also, during the compilation process, Hive Server 2 also needs to talk to the Hive metastore to get various information about the tables involved. For instance, like the partition information, statistics, and so on. So as we mentioned before, most of the code change for Hive on Spark happens in the task compiler and Hadoop client. So a task compiler takes the input of operator tree and produces a tree of tasks as a result. Each task is also described by work. So because task compiler is platform dependent, in Hive, before Hive on Spark, it has two types of task compilers, a MapReduce compiler and a test compiler. Correspondingly, there's MapReduce task and test task, which are described by MapReduce work and test work. So with no surprise, for Hive on Spark, we introduced a new type of compiler called Spark compiler, which generates Spark task from input operator tree. And a Spark task is described by a Spark work. So a work in Hive is basically a metadata for task. So a major difference between Hive on MapReduce and Hive on Spark is how work look like. For MapReduce work contains exactly one map work followed by 0 or 1 reduce work. But for Spark, a Spark work contains a graph of map works and reduce works. This is also due to a key difference between MapReduce and Spark. For MapReduce, between the stages, it needs to write intermediate result to temporary files. So it needs to have, but for Spark, there's no such restriction. And for instance, if you look at the query here on the left-hand side, this query does a very simple thing. It first do a select, and then does a group by followed by order by. For MapReduce, a query plane looks like in the middle. It contains two MapReduce jobs. Each job contains a map work and a reduce work. So here, in the second job, it needs to have an extra map work because it needs to read the intermediate result from MapReduce job 1. On the right-hand side, you can see for Spark, it only has one job, which contains one map work, followed by 2 reduce works. So for the Hadoop client, we add a new Spark client, which in terms of role is similar to the MapReduce client and test client. So when the Hive user first instantiate a session and submit the Hive on Spark query, a new Spark client is created and is associated with the user session. A Spark client does a lot of stuff. It can do job submission, job monitoring, error reporting, statistics, and so on. At the moment, we support almost all of the Spark modes. We support local cluster, standalone young cluster, and young client. And we support young cluster in default. So an important component for Spark client is called Spark context. All the previous mentioned functionalities for Spark client, like job submission, job monitoring, they're actually done through Spark context. However, Spark context is a little bit hard to use. First, it is heavy-weighted. So you don't want to put multiple Spark context in a single JVM process because that will add tremendous memory pressure on that process. Also, it is not thread safe. So you don't want to share a single Spark context between multiple Hive user sessions. So what we really wanted to have is so in Hive, what we want, because we have, it's very common in Hive to have multiple user sessions connect to the single Hive Server 2 process at the same time. So what we really want to have is to have a one-to-one relationship between Hive user session and the Spark context, and also to keep the Spark context outside the Hive Server 2 process. So that's why we introduced a context called remote Spark context. This remote Spark context is created and lived outside Hive Server 2. And in particular, in young cluster mode, remote Spark context lives in the young application master process. And for any other modes, it lives in a separate process other than Hive Server 2 process. So for instance, if you look at this picture, it has two users. Each user is associated with a separate user session and a separate application master process. And you can see there's also two remote Spark contexts. So in general, data processing in MapReduce looks like this. First, a new Hive job will read table from HDFS files using the MapReduce framework, and then it does the map side processing, and followed by then the output of map side processing will go through a shuffling process using the MapReduce framework, and followed by the reduce side processing, the output of which will get written to disk as either the final result and returned back to the client user, or as the input for the next MapReduce job. So you can see here, the map side processing, actually it just uses the map work and the reduce work we mentioned earlier, because each map work or reduce work essentially contains a fragment of operator tree, and the data will go through the operator tree and processed by each operator. So for Hive on Spark, the data processing is similar to MapReduce, but not quite the same. So in Spark, every Spark job starts with the initial RDD followed by a list of transformations. So each transformation is roughly just a function that takes an input iterator and produces output iterator. So in Hive, a Hive on Spark job also starts with an initial RDD, which is called Hadoop RDD. This is implemented in Spark. Then for map side processing, we use a transformation that is essentially a wrapper on the existing map work. So for this transformation, the iterator is essentially an iterator of rows or row batches in case of vectorization. And then the output from the map side processing will go through the shuffling process, which will use Spark's transformations like group by key, sort by key, and so on. And similarly, the output from the shuffling will go through another transformation, which is essentially a wrapper on the reduce work. And then the output will go through, we get either written to file or be processed by the next shuffle transformation. So a Spark plan is composed of those four components. There's a map input, which essentially is just a wrapper on the Hadoop RDD we mentioned in the last slide. And there's a map train, which is essentially a wrapper on the map work. And there's a shuffle train, which is a wrapper on the existing Spark transformation. And finally, the reduce train, which is a wrapper on the reduce work. So for the previous example query, you can see that the corresponding Spark plan looks like this. There's map input followed by map train, followed by shuffle train, and then another reduce train, followed by shuffle train, the reduce train. So you can find the correspondence between this and the Spark job that I showed before. So I think the advantages for doing this is that first, we can reuse many of the existing data processing logic in Hive. So because, as mentioned earlier, a transformation for Hive on Spark is essentially just a wrapper on the map work or reduce work. So underneath it's just, we still use the same operators in Hive. So I think there's no need to reinvent the wheels. Also, because of this, we can reuse many of the existing features in Hive, like authorization, window functions, UDF, and so on. Also, in future, if somebody implement another new feature in Hive, we can also probably get that for free. So about challenges, first, First, during the project, we found that there's a lot of missing features or functional gaps in Spark. For instance, we have this concurrent data pipeline issue. What this means is that in Hive, there's a feature called multi-insert. With multi-insert, a query can read from a single source table and having the data go through different multiple data pipelines and written to different output tables. So the benefit of doing this is that you only need to, even though there's multiple data pipelines, you only need to read a single source table once. So this is useful if you have if you have a huge source table and you don't want to do table scan multiple times. However, this logic is not that easy to express in Spark. In Spark, each input RDD, after going through a transformation, it has to produce exactly one output RDD. So, but in this case, we need to have multiple output RDDs. And an alternative solution for this is to have the input, to cache the input RDD, and then use that input RDD to produce all the output RDDs we want. However, we found that table caching doesn't really work in Hive on Spark. I was still trying to resolve the issue at this time. Also, this Spark context issue that we mentioned earlier. And also, Spark has two sets of APIs, a Scala API and a Java API. Sometimes for a particular API, it is only available in Scala, but not in Java. So we find that sometimes annoying. And finally, there's a scheduling issue, which we'll talk about in the next slide. Another challenge for us is that the large code base in Hive. So basically, before we started project, most of us are relatively new to Hive. And the Hive has a ridiculous large code base. So it took us some time to learn about details. Also, there are many contributors working in different areas and different countries. So coordination in the team becomes non-trivial. And finally, this library dependency conflict between Hive and Spark. For instance, in Spark, it uses JavaX Servlet 3.0, but in Hive, we use 2.5. So that's some issue we have to resolve during the project. So regarding the scheduling issue, so in Hive, it is very common to have a multi-tenancy environment where you have multiple user sessions share the same single Hive-2 process. So, and all those sessions, they may be very different from each other. For instance, you may have heavy user versus light user. A heavy user may submit a lot of queries in a short period of time, but for light user, it may just submit 1 or 2 queries, and then the session becomes idle for the rest of its lifetime. Also, you have big query versus small query. A big query may require a lot of memory and the CPU resources, but small query may not. So initially, Spark allocate a fixed amount of resources for all those user sessions, regardless of their characteristics. So this doesn't make sense. So we request a new feature called dynamic executor scaling. What this means is that it can allocate resources dynamically depending on the workload for each Hive user session. So initially, the Hive user session can get a small fixed amount of resources, and as long as the Hive user session has any pending task to run, the Spark will allocate more resources to that Hive user session. And once that Hive user session becomes idle, then Spark can reclaim all those remaining resources from the user session. So this is very useful not only for Hive, but possibly for many other Spark applications as well. So the current status for this project, basically we have implemented all the functionality. We have already finished the first round of optimizations, and we plan to do more optimizations and more benchmark against MapReduce or tests in the near future. And so also Hive on Spark is released in CDH 5.4, and in upstream it is released in Hive 1.1 and 1.2. And for future work, you can follow this JIRA to get more information. So about the optimizations we have done so far. So first, we have migrated all the existing join algorithms from MapReduce to Spark. This is non-trivial work. We spent a lot of time on that. Also, we have done some optimizations on the split generation. because in Spark, a Spark task is really cheap, so you want to have more splits than MapReduce. Also, we have enabled CBO and the vectorization. For those two, we don't have to do almost anything. So they come almost for free. And in the near future, we plan to do more optimizations, including table caching, which we mentioned earlier, and dynamic partition pooling, which we'll talk about later. So in summary, I think this is a community-driven project. There's a lot of organizations involved, and I think it can benefit a lot of users. So in the next, I'll invite Chen Xiang to talk about some benchmark results we have collected so far.
Okay, thanks, Chao. Hello, everyone. My name is Chen Xiang. I came from Intel China Big Data team, and our team have been collaborating with Cloudera and other community folks working on this project since the beginning. And just a few times ago, we have been done a TBCDS benchmark on Hive. So today, I would like to show the benchmark result. Oh, sorry. Okay. So first of all, my English is not very good, actually, so feel free to interrupt me and ask if I didn't explain myself very well. Our test environment has 8 physical nodes, and each node with 32 logical cores and 64 GB memory. And we connect all the nodes with a 10 gigabit network. For the components, we use Spark 1.3, Hadoop 2.6, and Tez 0.5.3. As the Hive Spark is still under active development, so we use the last git code in Hive Spark branch. Okay. We test the TBCDS benchmark on the 2 different datasets. The smaller one with 320 gigabyte dataset, and the big one with 4 terabyte dataset. And we test this TBCDS for Hive both on all the 3 engines Hive support, which includes the MapReduce, Spark, and Tez. And all these 3 engines shares most of the Hive configurations, except those configurations which is execution engine specific. And we try to enable all the possible optimizations in Hive. Okay. For the specific configurations, like Hive on Tez, we program the Tez container. We program 215 containers for Tez cluster. And we set the Tez auto reducer parallelism to true, so that Tez would decide the reducer parallelism on runtime. And we also enable dynamic partition pruning for Tez. For Hive on Spark, first of all, we launch the Spark cluster on young client deploy mode. And we assign each Spark executor with 5 gigabyte memory and 4 logical CPU cores. And we also allocate each Spark executor with 1 gigabyte extra off-heap memory. Besides that, we use the RZF as the Spark compression instead of default Snappy, as we found that the RZF perform better than Snappy in our tester. Okay, for data collection, we run each query 2 times and measure the second run. There are 2 other things to mention here. The first is that all the Hive on Spark querying clusters include the Spark cluster launcher overhead. So as we launch Spark cluster in young client mode, so we have to launch the remote Spark context process, and the remote Spark context would request resources from young and launch the execute processes and wait for all the Spark executors to register back to Spark driver. So that would take a while. So by the way, for the Hive on Spark users, as Charles has mentioned before, that Hive will only need to launch the Spark cluster the first time you run querying. And for the second or the following queries, Hive would just reuse the existing Spark cluster. So for the interactive queries, Hive on Spark would respond in seconds level latency. The other one is that as Hive on Spark has not implemented the dynamic partition pruning optimization yet, so for fair comparison, we also measure a few queries for tags which benefit from this optimization with the dynamic partition pruning disabled as well. Okay, so this first chart, we compare MapReduce and Spark on 320 GB data. The blue one is for MapReduce, and the yellow one is for Spark. As you can see that Spark overperforms MapReduce in all the queries, and all the queries here. And in the next slide, we add tags into this chart. Tags is also outperform MapReduce in all the queries we tried. And but compare Spark to tags is hard to tell. There is some queries that Spark is faster, and there is also some queries that tags is faster. So we found these 3 queries which tags is faster, and during our further research, we found that tags benefit from the dynamic partition pruning a lot. So that's why it's faster than Spark on these 3 queries. So what dynamic partition pruning is actually? There is a common case in Hive that a big table, which is partitioned and joined with a small table on the partition key. So in Hive, if dynamic partition pruning is enabled, Hive would first scan the small table, do all the filter and projection operation to generate a partition key set. So then while Hive scans the big table, Hive would check that if the current partition key exists in the partition key set. If not, this means that there is no this partition key is not appears in the small table. So Hive does not need to scan this partition. So as this partition key set is generated in the small table, and there is actually sometimes some filter conditions. So this partition key is quite small. And so Hive would skip a lot of partitions during scan the big table. So this will save a lot of disk I/O cost, and for the CPU and memory cost in the computation phase. And this optimization has not been implemented on Hive on Spark yet. So Charles is actually working on it. We add this recurrence cluster for tags without dynamic partition pruning as well for clear here. And as you can see that without this optimization, Spark is perform closer with tags. Okay. So we compare MapReduce and Spark on 4 terabyte data in this chart. And similar as the previous small data set, Spark still outperform MapReduce a lot, almost every recurrence. And we compare Spark and tags on 4 terabyte data. For this 3 recurrence, okay, so tags still perform better than Spark due to the dynamic partition pruning optimization I have just mentioned before. And we also add the curing cluster of tags without dynamic partitions. As you can see in this chart, actually tags benefit a lot from this optimization. And without it, Spark is slightly faster than tags actually. So there is also other currents which we found that Spark is faster than tags. And a common case is that map join. Hive Spark done a lot of optimizations on map join, and during the benchmark, we found that Spark is actually faster than tags on many map join related currents. But we also found some currents that tags is actually faster, such as the common join related currents. Okay, so I think we can summarize here. The first, in general, Spark is a few times faster than MapReduce. I think that's for certain. Second, Spark is as faster as or even faster than tags in many currents. And dynamic partition pruning optimization is a very important optimization. It helps tags a lot on certain currents. And without this optimization, Spark and tags are close on these currents. And tags is faster than Spark on certain currents, such as the common join related currents. And I'm not sure if you have noticed that we found that actually Spark performed better on the 4 terabyte dataset. And about the dynamic partition optimization, the choice working on it is under very active development. I suppose it should be ready. It should be available in a very near future. Okay, thank you, and that's all. And if you have any questions, please feel free to ask. Thank you.
Question?
Hi. So are all Hive queries now going to be translated into a single Spark job, or are there cases where there'll be multiple Spark jobs for a single Hive query?
There could be cases that we have multiple Spark jobs. For instance, in map join, we could have more than one Spark jobs.
Okay.
Yeah. Can you go to the microphone? I can't hear you. Sorry.
Yes, about the benchmarks. I'm curious, it looks like you chose 13 of the 99 queries of the TPC-DS
Yes.
benchmark. Why those 13? Why not all 99?
I think we just, yeah, do you have?
I'm sorry,
The TPC-DS benchmark has 99 queries, but looks like you chose 13 of those. Why just 13? Why not all 99, and why those 13?
Okay. we're trying to pick different kinds of TPC-DH currents. For example, we choose some currents that use map join, and we choose some use common join. So, yeah, so there is we try to avoid that list all the currents of the same time.
Also, there's only a subset of TPC-DS queries available in Hive.
Yeah.
So because we have to adapt the TPC-DS, our original TPC-DS queries to Hive, and some of them may not work.
Okay. And the other question was on the database size you used. There's certain standard sizes that you seem not to be using. You use 300 gig and 4 terabytes instead of like 3 terabytes, which is one of the standard accepted sizes. I'm wondering why is that?
Actually, there is not much consideration on that. We just run to a smaller dataset and a bigger dataset.
So it happens to be...
Yes, so it happens to be like 4 terabytes. I don't think that's have much difference between like 3 terabyte or 4 terabytes.
Okay, thank you.
Yeah. Hello?
So how are organizations migrating from MapReduce to Spark? What is the migration path, and what efforts do they take?
So to enable Hive on Spark is pretty easy. So assume you have a Spark cluster already, and then you just need to in the Hive CLI or beeline, you just need to set Hive the execution engine to Spark, and that's it.
Experience perspective, what all the disruptions that people have seen when they actually do it?
The instructions.
Is it as smooth as just pointing to the new execution engine, or are there any disruptions that have come to light?
Sorry, I didn't hear you. Sorry.
So you just said that all that has to be done is to change the execution engine, underlying execution engine.
Yeah, there's also some setup you need to do. We have on upstream, we have a document. It's titled Hive on Spark Getting Started. You can check the web page for more details.
Okay, so there's absolutely no disruptions that have come to your notice when people move from traditional MapReduce engine to Spark?
Yeah, you just have to follow that documentation.
Oh, really?
It has all the instructions how to do that.
Okay, thank you.
Yeah.
DPP applied on which field? Is it a date field or any string field?
Say it again?
The DPP applied on which field?
Which tree?
Which field?
Or which field?
Yeah.
Oh,
like is
yeah.
it a date based or timestamp based field or?
You mean the TPC-DS query?
Yeah.
Actually, I didn't understand the question.
Yeah, I think it's on a date.
Okay.
It's on a date field, yeah, because that date is not a partition key, so you have no way to optimize that statically. You have to optimize it dynamically using dynamic partition pruning.
Okay. Do you think if
you
DPP
mean
is
the
applied?
dynamic partition pruning?
Yeah.
Why is dynamic? Do you want to know why we have to decide dynamically on runtime, right? So that's because
it's applicable to any data type, or it's a particularly for only data?
For any data type.
for any type which is partition key. Yeah.
Okay.
So that Hive can filter the partitions which is not in the partition key set.
So the results will be same, irrespective of string or date. The result will be same, or
if the partition key is not in the partition key set, that means that the partition key set is generated from the small table. So this means that this partition key is not appear in the small table. So since it's a big table join the small table, so you don't need to scan the partition of the big table.
Okay, thank you. Thanks.
One question here.
Hi.
How would you compare the performance of Impala versus Spark? I know you didn't benchmark it, but
Yeah.
I'm curious.
We get this question every time. So we haven't done any comparison between Hive on Spark and Impala, and I don't think that's on the roadmap as well. So our main focus is on comparing Hive on Spark with Hive on MapReduce at the moment. Yeah.
Hi, you were saying that both Hive and Spark do the map. Is there any difference in the way that you go about doing the map step, or are they pretty much the same?
You mean the map work?
The map work. Mm-hmm.
Yeah, I mean, so first of all, for both MapReduce compiler and Spark compiler, the input is almost the same. It's the same operator tree. But, the compiler does different stuff. It breaks the operator tree in a different way. But the final result, it always have the map work, but the content for the map work may be different.
So is Spark a little bit quicker in the map step, or is it just about the same amount of time?
It is quicker, I think.
But the real savings is the reduce, right? Is that what you're saying? Because Spark does everything in the memory, right?
Yes.
Whereas Hive does it on the disk.
Yeah,
and
so the
writes out to
shuffling
disk.
stage, in terms of the shuffling stage, Spark is much quicker than MapReduce.
And because it's doing it in memory, right?
Yeah.
Yeah. So that's where you get most of the savings in your time, is in that step, right?
Yeah, I think so.
Okay. Thank you.
Okay.
Okay.
Thank you.
Thank you.
这个